So welcome all. This is Nitin Ramrakhiyani. I mean, I work with TCS Research. If you followed Ankush notifications, you might have seen a link to my like WordPress website and would have found out more about me, obviously. So I don't think an introduction is in place. The more important thing is that I am a DAIICT alumni, and but I did my MTech long back in 2013. I mean, finished in 2013, and then have been associated with thesis research. Um, and we do. I mean, many people don't know that. Yeah, TCS has an R&D department as well. So it does have, and I am working there. And so we are doing lots of things there. Like there are some groups that are in robotics. There are some groups that are in image processing. We are particularly interested in text mining, NLP, and what a time to be a part of that, right? I mean, it's fearsome also that GPT-4o might do something with our jobs versus it's opportunistic as well, right? So let's see. So I'll just talk about a paper that we recently submitted and then got accepted at EACL. And the title of that paper is Why Generate When You Can Discriminate? A novel technique for test classification using language models, right? So like towards the end of the talk, you will come to know that what was the motivation of doing this kind of an exercise, and also give you a glimpse of what kind of things we do, right? So jumping in, like what is text classification, right? So the task of assigning one or more applicable class labels to a given piece of text, okay, be it a sentence or a paragraph or a phrase, is basically what we call is text classification. But the task that we boiled down on was to use a causal, which people also call autoregressive or decoder only, whatever you want to call, a causal language model to perform text classification. Okay, so we are not looking at BERT-like encoder models. Okay, we are going to look at more generative ones like GPT-2 or GPT-Neo, GPT-J, something like that, or even for that matter, ChatGPT, which are all generative. And so once I say this, right, that we have to do this, right? So we have to do text classification and use these kind of things. What ideas spring up in our mind, right? So you might be reading about lots of things, right? So some quick ideas that come to our mind are to train a classifier, right? Be it a standard classifier or a neural classifier, or fine tune a transformer, right? The other idea that comes to your mind may be, okay, why not write a prompt? Okay, just do it zero shot. We don't have training data. Construct a prompt and try it on ChatGPT or GPT 3.5, Turbo, whatever. Or if you have access to some examples, then include some examples as part of the prompt and do some kind of in-context learning, right? So you tell it, give an example of some classification, instances where you have the text and you have the class. You have a text, you have the class, okay? And you give such examples and finally you get an answer on your test sentence or test instance. So these are some ideas that quickly spring up in the mind, right? कि कुछ text classification करना है, so we'll do this. But like what motivated us was some issues with these ideas that could come to your mind, right? So if you want to train a neural classifier or fine tune a transformer, right, obviously it requires training data. And also if you are thinking of fine tuning a transformer, then you will need some specialized hardware, right? But more importantly, this kind of a technique is not robust to technical changes. I mean, technical in the sense, I mean, non-technical as such, but technically non-technical. Like if I change the number of classes, right? If I change the semantics of my classes, if I add another class, right? Or whether sufficient training data is available. Okay, so there are these kind of corner or boundary challenges that you would face if you are thinking of training or fine. Acha, if you want to do zero shot on ChatGPT, so there are privacy concerns, right? Because I won't like to send something on the net to a API which is probably listening to what I am telling it, right? Or it's even building data sets out of it and then putting it outside. So there are lots of privacy concerns surrounding the use of ChatGPT itself, right? We all know that. And if you come to my side of the picture, there are many people, there are many customers that we talk to. They say that, no, we prefer a local deployment. Right now, they can't obviously have a local deployment of ChatGPT, right? So what they'll say is, okay, can you do that with a smaller model, right? That we can deploy on a smaller GPU. So this kind of local deployment is preferred. And in the zero shot case, another observation that we have seen is that smaller models generally. So now, okay, if I say, okay, chalo chat GPT use nahi karna hai, let's go for a smaller model, but they are more prone to hallucinate. Okay, you can find some examples in the link of the paper that I had shared, exactly our paper, on the SST2 dataset, which is a sentiment dataset, which tries to classify the sentiment of a movie review. And there what they say is that if I ask it that, okay, you just say whether it's positive or negative, it will still say it's messy, it's unintelligent, something like that. So it's not giving me positive or negative. Okay, so maybe it's hinting towards the right thing, but it's not really helping in the classification. And sometimes obviously it hallucinates. Then in the few short case, suppose you build some training examples. Okay, k equal to 18, k equal to 16. Okay, so you give it 8 examples, 16 examples, and then you try. So that's good, and many a times that works quite well. But then what will happen is, suppose you have training data. Okay, suppose you have training data, the context window of the LM won't allow you to fit all that data as examples in your few short prompt. Okay, so the context window basically restricts this number of ICL examples. So then looking at all these things, we thought that, okay, what is the way out, right? Can we think of a way out, right? So that is a solution that I'm going to present. Okay, so hope the motivation is clear. Okay, and if you have questions, you can, I don't know whether I'll be able to see raise of a hand, but Ankush, maybe you can prompt me, and stop me if there is any question that somebody is trying to ask.
Sure.
Yeah.
Please feel free to type it in chat, and I'll be able to relate to it.
Yeah, correct. Yeah, just then stop me then. Okay.
Sure.
Okay, so what is the outline of this proposed approach? So we try to divide it into 2 steps. First, we generate some features using the LM, but they are not standard embedding based features. Okay, they're slightly hatke from that. Okay, those are basically perplexity and log likelihood features from the LM. Okay, and how we compute it, maybe I'll not go into the details right now. I'll just tell it when I'm discussing in that. And then step 2 is basically to learn a classifier on those perplexity and log likelihood features. Okay. So right now at this stage, you just understand that, this is a 2-step process. In the first step, we elicit some features. Features are not standard embeddings or, word vector kind of things. They are something different. And the step 2 is learning a classifier. Now that learning the classifier is a very lightweight classifier, like logistic regression or support vector machines. Does not involve any fine tuning. Okay, so you're not touching the pre-training of the underlying LM. Okay, so that is where and then you will towards the end of the talk you will be able to relate, okay, how the points that I wrote in the previous slide, how all of these are being tackled. Okay. Okay, so first, let's revisit some background. Okay, let's spend some 10 minutes on this and then we dive into the approach. Okay, so first of all, let's understand what are key phrases. So because they are a pivotal component of our approach. Okay, so what we assume is that whenever you are given a classification problem, okay, you will be told about what the classes are, right? Or you can guess what the classes are, right? So can you represent each class using a set of key phrases, okay, or some things or some phrases that define the class? Okay, so for example, in case suppose the name of the class is business, then you can use things like business, stock market, banking, monetary investments, economy, income and expenditure, corporate profit and loss. So now words like these to indicate business. So it's like these are descriptors of that. And then there is or some other class from some other data set, means of transportation. So then there is a vehicle, a car, a train, an aeroplane, a ship or a boat or whatever, right? So you can describe the class using these kind of key phrases, right? So it's simple, pretty simple, right? It's like describing the class. And in case when the classification problem is challenging, right, then the key phrase can be obtained from domain experts also, right? So now I'll show you a specific use case that we tried, which was on audit data sets or audit reports. Okay, so audit reports are basically, there are auditors. If you know about this fact, there are auditors who audit a company's financial performance. Right now, when they are auditing the company's financial performance, they write a report. Okay, and in that report, they capture about lots of things. Maybe I'll tell about the use case later. But then that's a very niche use case where the kind of classes that will be involved will be very, very involved. They won't be as simple as business or means of transportation. They will be like payables, fixed assets, inventory. Now you don't know the meaning of these things unless you are a domain expert, right? So then you can ask a domain expert, okay, how do you define fixed assets? Okay, how do you define inventory, right? What are the terms that you use for inventory? Okay, to wo kuch bolega, go down or something like that, right? So those key phrases you can obtain from domain experts or the one who is explaining you or giving you the classification, right? So key phrases basically are relatively easy to obtain. Now, if you have read into this area, then you would have come across these two papers called Prompt Exploiting Training or KPT, which is Knowledgeable Prompt Tuning. Right? These are two pivotal papers. One is by Schutz, Henrik Schutz, and his student Tim Schick. I don't know how they pronounce it in German. And then there is this Hu et al. Right? Who did Shaodang Hu or something like that? Who provided this KPT. So what they did was they did something similar, or they have done something similar earlier, but they have done it for encoder models. And an important difference that they have, and like we have from them, is that they only support a single word kind of a key phrase, right? Because if you are aware, encoder models such as BERT or Roberta are generally trained with a masked language modeling object, MLM objective, and where the thing is to fill a token, right? I mean, fill the correct token at the mask place, right? So that only allows a single word, right? But whereas our approach, if you see the key phrases that I have written here, they can be of any size you want, right? Monetary investments or corporate profit and loss, right? And neither of them can be expressed as a single word also, right? I just can't have profit and loss if I want to combine in one phrase, or say, for example, monetary investment. Now I can't use one word for that. It will be very limiting. Okay, if you think of one word, then how do you define this, right? So our approach basically allows this kind of flexibility in these kind of descriptions. Okay, so that is one important difference that we have from these. Right? Why I'm adding this here, because some particular reviewer had pointed this out, that you should mention this relation with PET or KPT, which are already established techniques. But yeah, we had our own differences, and they don't use perplexity or log likelihood, so we had the novelty. Right. Right. Now let's talk about perplexity and log. Yeah.
Nitin, sorry to interrupt.
No problem.
Based on previous lecture, so we have a couple of questions. Can you take it right now?
Yeah, sure. So,
yeah. So Tarang is asking, are the words business, stock market, etc. Describing the business generated by machine, or they are human curated?
Human. Obviously human. Because see, it's like this is part of designing my solution, right? So if I know the set of classes, then it is the designer or the one who is devising the solution for the classification, who is kind of describing these words, right? And this basically gives you the flexibility, or the designer the flexibility, how the person wants to describe the class. Okay, so there is and always that the DEA approach, right? The data exploration, or something that one does on the data once you receive the data, and once you observe what kind of classification is happening, what the text talks about, what terms the text talks about, what the class will look like, right? Once that is there in the mind of the designer, then fetching or gathering these kind of words is not a difficult task. On the other hand, I mean, I'm just to add to that, there are other ways you can also learn these things. Okay, so of course we have so you will see in the future work, I have kept this as a future work, that what is how to find the right set of words for a thing. So one hint that I can give here, if you know about latent Dirichlet allocation, LDA, which is a topic model, right? Topic modeling, if you see, so you can use topic models to have a handle over such kind of words. Okay, so that is also another way to go about by fetching these kind of key phrases. So basically, I mean, primarily in our current this thing, or in the current work that I am demonstrating, these are all handmade, but then they can be generated automatically. You can use LMs also. You can use topic models, various other things.
Okay.
Yeah. So hope that answers the question, I think. Yeah, I mean, if there are questions, then again we can take them. But yeah, I mean, maybe one at a time. Go ahead.
Sure. So Perhaps you can take the remaining question
Yeah.
towards the end.
No. You can go on. If there is another question, then I'll take it right away. Otherwise,
Sure, sure.
maybe any
So,
follow-up question that we can take at that.
sure. So Parth is asking, how can you control key phrases related to a domain?
Excellent. Right. So we did some kind of ablation at the end. I'll show you where we try to vary the number of key phrases. Okay. So initially we said that okay, we fix the maximum number of key phrases for a certain class to be 10. है But in most cases we found out that you basically are not getting even 10 key phrases to define a class. The ones that I'm just even in means of transportation, I have used how many? 1, 2, 3, 4, 5. 5 key phrases. Okay. So we kept a limit of 10 key phrases, but as such, there is no limit on the key phrases. You will see as part of the approach that there is actually no limit on the key phrases. But like when we tried to see what is the impact of varying the number of key phrases, we found out that at a certain level, right, after 4 5 key phrases which are most descriptive of the class, if you just include those, then the performance basically starts plateauing. Like adding more key phrases are not adding more value, like they are not bringing any jump in the thing. So basically maybe I'll show that graph in the end, but right now we can be content with the thing that there is as such no limit. But after if you give really good key phrases, then then it'll still hold the fort. Okay. Thanks.
Cool. So Vimal is asking, can we treat the key phrases as some sort of weak set of rules that should be present
Bilkul.
to ensure?
Very good insight. Yeah. Exactly. We can. In fact, if you try to tweak the approach a little, once we go through the approach, you will realize that you can also use regular expression based patterns and then also try something using that, right? So and elicit those perplexity and log likelihood features that I'm going to explain about. You can use even regular expressions in some manner in the approach to get that. So you can have some sort of rules, and of course these are some sort of rules in a way. But if you want more complex rules, also you can bring them in the approach. But one has to just think through a bit. But I believe that is possible.
Cool.
Yeah.
So
should I move on now?
I would request participants to, if you can paste your question directly in the Q&A section. So it's like it will be available as logs later on also to other participants. Please carry on.
Yeah. Okay. Thanks. Okay. So So coming to perplexity and log likelihood, that's the what should I say heart of this whole thing. So if we read our textbooks, right, the speech and language processing by Jurafsky or our introduction to information retrieval by Manning, Raghavan, Schultz, they say perplexity is used as a metric to evaluate language models, right? But if you really sit down and see what is perplexity, it's basically measuring some kind of plausibility, right? And that was our proposal, right? We try to use perplexity for a slightly different purpose, not as an evaluation metric, but to judge the plausibility of a text fragment using a generative language model, right? And then use that further in the form of some mathematical fraction to compare multiple such text fragments and decide which one is the most plausible. Okay, so it's a slightly different interpretation of perplexity that we are using. But to tell you what is plausibility of a text, we mean that it is more seemingly reasonable or probable in that context. Okay, so if you see the example, right, the second in command of the Shiv Sena UBT is Sanjay Raut, is obviously more plausible for an LM which has read lots of news and seen this than saying the second in command of the Shiv Sena UBT is Nitin Ramrakhiyani. Obviously, right? So that kind of plausibility we are looking at. Okay, that whatever I say or whatever I append here or whatever I place at this place should fit in well with the context, and it's more plausible, it's more reasonable, it's more probable to arrive at that place. Okay, so we are trying to measure this kind of plausibility using perplexity. Okay, right. Anyway, I would refrain from remaining with Shiv Sena UBT. Sorry. So that was a digression. Okay, so now let's get into a little bit of the math behind this. So let's consider a text fragment X, which has n words, right? Okay, n tokens, you can say. And the perplexity of X is defined by this formula, where you can also consider this as like seeing the word wi when I have seen the back context. I mean the words that are less than I. Okay, so this is that same probability, conditional probability that we have been seeing from ages, where this word, what is the probability of wi occurring, wi minus 1, wi minus 2 till w1. And I just raise it. So basically, you can raise it to minus 1 by n. Okay, I've just opened that here, and you take a multiplication over all these terms, right? So you vary I from 1, 2, 3. For 1, it won't be there, but for 2, it will have 1 as its context. For 3, it will have 1 and 2 as its context, right? That. And we have seen, what is that called? Markov assumptions, where we have a limit on that, right? So you just have 2 tokens, or a bigram language model or a trigram language model, right? So these are the, but in a what should I say, in a more basic form, this is what perplexity looks like, right? And I can condition my perplexity, right? So the conditional perplexity would simply be something like X given C. Okay, so nothing different here. I'm just appending C, C before my words, right? So I'm just trying to say, so it's like C1, C2 till Cm, and then W1, W2, W3 till Wi minus 1. And what is the probability of seeing Wi given the entire context? Okay, so there is nothing different. I'm just adding C before the X, right? But what perplexity is, right? So we say, I mean, the textbooks say, and yeah, that is what we have observed, that lower the perplexity, better is the plausibility or probability or reasonability of the text in that context. Okay, because perplexity, even if you see its English definition, perplexity means confusion. So if the language model is confused for a certain text, then it'll be jittery. But if it is quite certain that yeah, okay, iske baad yahi aayega, so then it is less perplexed, less confused, and more probable answers are, more plausible things are generated. So now, how do we relate it to log likelihood? Okay, so and log likelihood and conditional likelihood are defined slightly differently, where we just put this term that I was just explaining before and a log over it, and then we do a summation over on all the things, right? I equal to 1, then I equal to 2, 3 till n, and I just do a sum of the logs over this, right? But on the right hand side, I've tried to establish the relation between them, right? So if I just do this, so as this is what I was telling, that you can keep this as minus 1 by n, right? Now you do a exponential logarithm kind of a inverse here, and then you will be able to figure out that this this is some bit of algorithmic algebraic jugglery that I've done, but I've just tried to put the exponential here, and if you see exactly this part is something which I'm considering as the log likelihood, right? So they both are related, but maybe I'll not be touching upon in this particular this thing, but you can have a look at the paper if you are interested, that why we considered both log likelihood and perplexity features, both why we considered them differently. Okay, but there is a subtle reasoning behind that, right? And that is to do with the tokenization issues, right? If the tokens are different, then the perplexity and log likelihood values will be slightly different, right? If the splits in the the splits of the words that the tokenizer does into subwords or word pieces, that actually hinders the computation of both of them, and both of them arrive different. So that's why considering both log likelihood and perplexity are important. But more details you can find in the paper. I may not be having time to talk about that. On the other hand, so higher the log likelihood, better is the plausibility, right? You can see that, okay, from the relation. So here it was this, but now it has taken, it's on that end, right? Yeah, and one more interesting background or piece of background that I would like to give is that now in the literature, right, people are putting different size bounds. Okay, some say that yeah, okay, you consider small LMs as some things that are less than 10 billion parameters. And there are plenty of things that are going on here, right? Apple's OpenELM, Tiny, Llama, GPT-2, Excel, Neo, 6 billion, Mistral particularly, like our recent things are telling that Mistral 7B is a class apart. It's much better than its 7 billion counterparts such as MPT, OPT, Falcon, Mistral is way better, though it's an instruction tuned model. And then they say that yeah, medium LMs are like 10 billion to 100 billion, like the 20 billion, 30 billion, whatever parameters. And then there are really large things, right? 775 billion, Bloom and Palom. I think there was some 532 billion one also. So yeah, so why I kept this, because our focus is particularly on this, because of the constraint that we want locally deployable models, right? Even for these kind of models, you need very high capacity of GPUs or even distributed GPU networks, right? But people are not willing to invest in that, and hence this becomes an interesting area of research, and that's why you see many people are, and there is this gold rush towards small LMs now, right? Phi 2 is a very small model, but it is doing quite well. Phi 3 has come out now from Microsoft, right? So, right now we come to the actual approach. Okay, so we are too deep into the thing, but yeah, I'll try to rush a bit, but try to also maintain that you get some takeaways. So let's go to the formal problem definition, right? So assume that L1 to LC is the set of class labels, okay? And each class label, okay, each label is described by NI key phrases. Okay, so there is P1, P2, P3 till PNI key phrases describing each class. So for the ith class, I am saying it's P1I, P2I, PNI, right? That. And there is this X, which is of course to be classified. And there is a causal decoder only language model that I have, which is M. Now output is one or more classes from the L which are assigned to X. So I'm just considering that this as a multi-label, generically multi-label. Single label is a special case of multi-label. And now for the training regime, so there is the step 2, which is of creating the lightweight classifiers, is an optional step actually. If you have training data, you can go to step 2. Otherwise, in step 1 itself, you will get a zero-shot classification. But if you have, then you can consider a small set of training examples. Now we consider at most 500 training instances, okay, from whatever. So we have data sets that we have considered that have large number of training examples, but we only considered 500 just to show the utility or the efficacy of the approach. And we also show in the ablation that 500 seems to be sufficient. Even at 100, 200, it starts plateauing. So that's right. So now how do we generate these features, which I have been talking about? How do we use these log likelihood and perplexity values to generate the features? Okay. So now let's look at this very closely. This is the the real heart of the thing. So now X is the text to be classified, right? I'm introducing this thing called X, which is a connector sentence. Okay, which is just saying, which is exactly like this text is about, and then a key phrase comes here, right? So the key phrase is not part of the connector sentence. Beware, okay? Only this green part, this text is about, is my connector sentence, okay? Now, so what I do is for each of the class labels, okay? So now I am having X with me, and I have to see which class this X belongs to. So I take each class label, I take each key phrase of that class label, okay? So for each class label, I have key phrase. I take each key phrase, right? Suppose it is PJ, the jth key phrase of the ith class, the jth key phrase of the ith class. And I try to generate this kind of a fraction. Okay, so now just look carefully here. Right? So I am saying X plus S. So something like the text and the connector sentence is the conditioning part. So I'm just saying that okay, this is my W less than I. Okay, the equation previously that I was saying. And how likely is the key phrase given this context? Okay, so this conditional perplexity I'm trying to find. Very gelling like, and this over if I just have my key phrase. Okay, so now if you see here, right, if I give the context, yeah.
Hello,
yeah.
Sorry to interrupt, Nitin. So we are facing some disturbances. Is anyone else also facing a glitch in sound?
Yeah.
Yes. Perhaps we can try disabling the video.
Okay, yeah, that will be good. Wait. Okay, better now. I don't know. Then I'll go ahead. If you still face trouble, then you let me know. Or I'll just.
Sure.
Yeah, is it better now or not better, or tell me?
Yeah, it's better.
Yeah, it's better.
Okay. Okay, I've opened the window as well. So let's see if there is some issue with the. But then just beware of some noise at my end also, of some pigeons. Okay, is it better now?
Yes, Nitin.
Okay.
You're clearly audible.
Yeah, wait. Okay. So I'll just explain this part once more, so that we are not lost here. Yeah. So again, like if you see this kind of a feature, okay, it's a fraction of perplexity with the which is trying to see the key phrase in this context, and which is trying to see the key phrase as is. Okay. So now basically what I'm trying to do is that if I give the key phrase some kind of context, okay, context which is actually my text to be classified, right, then whether the perplexity goes down or goes up, right? So if the key phrase is not suitable to the text segment or the text to be classified, then it won't fit and the perplexity will be high, right? But if it fits, I mean, if the key phrase is suitable to its context or the text that is to be classified, then the perplexity will be low. So what happens here is that if I basically want this particular fraction to be as low as possible, if it is low, then this particular key phrase is optimal, is suitable, and hence the corresponding class is also suitable, right? So this is how this is devised. Okay, so to give you an example, so the text to be classified is something like Indian stock markets gain on the third consecutive day, and it says, and then I attach my connector sentence. This text is about, and then I expect this to be economy, right, as the key phrase. And then this is the numerator, right? So in the denominator, it's only this text is about economy. Okay. So basically, I'm trying to say that if I give this sentence as the context, whether the perplexity goes down or not, okay, whether it's really hinting me and this particular key phrase is really a fit with this kind of a thing. If it is, then yeah, this is the class I'm really talking about. Okay. And similarly, in case of log likelihood, as we are in the so now we are no more in the, so we are not taking if you remember, perplexity is basically a multiplier, right? But here log likelihood is a sum, right? So we are just a moment. Yeah. So now here what we do is we just take a subtraction of x plus s and the one without any context, right? I mean, basically this connector sentence context. Yeah. So if you see this example, right? So now here the text to be classified is expansion slows in Japan. Economic growth in Japan slows down as the country experiences a drop in domestic and corporate spending, right? And now there are various class labels that I have, like sports, which are described by key phrases such as sports, a sporting event, a sports person, or business, which is business, economy, stock market, science, space exploration, software, science, whichever, right? And then I build something like this: expansion slows in Japan, economic growth in whatever this news is about. So then I say sports, a sporting event, business, economy, science, space exploration, right? So I'm trying to fit every class ka every key phrase here, and then I'm trying to compute my feature values, right? So if you see here, now I want my perplexity based feature values to be lower, right? So if you see here, it's 1.22, right, which is lowest among all, right? Or even for economy, it's even lower, right? But if you see for this particular class, the key phrases are bringing the perplexity down, and that is what is desired, right? And similarly here, in case of likelihood, I want them to be higher, right? And 0.95 is higher If you see in all these set of values, or minus 0.4 is even higher. I mean, second best if you see here, right? So in this way, we are trying to, find out or elicit these features, right? So now you will get these values basically, right? This 3.48, 1.42, 1.22, 0.62, 7.12, 1.52. So you are kind of building a feature vector based on these perplexity values for a certain text. Okay, so this kind of a feature vector is being created. This is another part of the feature vector that is getting created. Okay, so this is how we are eliciting the feature values. Okay. And then we add some class level features also, right? Which is like, just what is the minimum of these values. Okay, so that is also added for each class. Okay, so for sports, what is the minimum? So in this case, it will be a sporting event. For business, what is the minimum? Okay, so it's 0.62, so then it will be economy. So we again, like we just repeat this 0.62 again. We repeat this 1.42 again in the feature vector. We repeat 1.52 again in the feature vector. This is just a class level feature. Okay, so for each class, that means for the ith class, I am taking a minimum over my key phrases, all the J key phrases, and then just adding that as a feature. So now you would argue that like classification to ho gaya. You found out that yeah, okay, this one is minimum, so you just assign it to business. Exactly, that is the zero shot classification, right? I didn't use anything, right? I just used the LM. I found out these feature values, and I just said, yeah, okay, this is my class. Okay, so that is exactly the zero shot classification. It is simply considering the minimum or maximum of the feature values, maximum in case of log likelihood, minimum in case of perplexity, right? So you can always take this. Now there are various things, right? In case you want to, it is, if it is multi-label, you can say, okay, the class that is second best in the feature values, right? You can assign that as well. Second best in terms of log likelihood, it will be second lowest, I mean second highest, I would say, if we assign order it in ascending order. So in this way, you can have a threshold on these values and then emit a certain set of classes which are most probable. Okay, for based on these feature values. So in this way, you can achieve a sort of zero shot classification, right? So you took a text, use the LM, find out these kind of feature values, order them, and say, okay, this key phrase is the best, and this does my job. Right. Now the second step is to learn the classifier. Right now, this is, as I said, it's an optional step and only necessary in case you are looking for a supervised setting. That means you have training data. Okay, and the now for all the training data that you have to generate the perplexity and log likelihood features, build that feature vector that I was talking about. But then there's an interesting thing here, right? So we do some kind of horizontal scaling of the features. Okay, so now this is, you can see this analogous to layer norm. If you know about layer normalization, it is some sort of layer normalization. There are no layers here as such, but it's like at an instance level, I'm trying to do some kind of feature scaling. Okay, it's different from the batch scaling or the min-max scaling that I generally do, right? This is different from that. At an instance level, I'm trying to weigh the features. Why? Because the comparison is between the features and not across the instances. Okay, so this is a slight nuance here, that we do a horizontal scaling, some sort of instance-based scaling of these features to capture all the relative variations, right? So obviously I have to compare, and hence I do this horizontal.
So, Nitin,
Yeah, yeah.
Can you please elaborate with an example? Like, what does horizontal scaling across the instance?
Yeah, so see, now what will happen is, so I come to this, right? So now here, the values that you see here. So assume that we have a 3-class classification here, and these are the two particular key phrases for each class. So your feature vector is basically just this or this. I mean, so the overall feature vector is basically a concatenation of the PPL values and the LL values, right? Now my horizontal scaling would simply scale at this level. That means it will capture the mean of these values and then subtract that mean and then divide by, so x minus mu by sigma that we do here, right? Why I'm doing, so now I did that at an instance level, right? I did this for particularly this x. For a different x, I'll do this again. For a different x, I'll do this again. So I'm just computing the mean or doing the scaling at an instance level. I'm not changing it. I mean, I'm not doing it at a Generally what we do in min-max scaling is that we do it in a batch, right? Or at the whole data set level. We compute the mean and we subtract it from all feature values, right? But we don't do that here. We do it at an instance level. Okay, why this is important? Because the perplexity values or the log likelihood values are very instance specific. They are not at a generic level, right? The features are not getting computed at a I mean, you can't compare the perplexity values or the likelihood values for one instance, for one text and another text. There is no real comparison between them. Perplexity is not a 0 to 1 scale business, right? The LM can produce any value. So you have to do that at a instance level, because the main fun or the main goal is to compare amongst these and not compare across instances. We need a solution at an instance level. We need to do the classification at an instance level. So the comparison has to be among these values. And I want these values to be normalized. That is my goal. Okay.
Clear.
Yeah. Okay. Okay, right. Oh, so now once I do this horizontal scaling, then I have a vector, right? The log likelihood set of values for all the key phrases of all class labels, and the perplexity values for all labels, I mean all key phrases of all labels, and the class level features that I just told. And then I have this vector, and then let's learn a logistic regression. Let's learn a support vector machine on that. Right? Who stops us from learning? Now, who stops us, or what stops us from learning larger classifiers? You are free to do that, right? We explored a bit of multi-layer perceptrons, but we found LR and SVM to be doing better, and hence we stuck to only these two approaches in the paper. But you are free to try lots of things. You have a feature vector, and then it's like a canvas in front of you, and you paint any classifier on the top of that. And there was a slight constraint that we also wanted to be resource friendly, and hence we only allowed or remained with these kind of classifiers, which is perfectly all right, and nothing stops us from learning these kind of simple classifiers also. You have a data, I mean basically some float values in a vector, and then we use LR or SVM, and it does well, right? Now, if you see here, there is no limit on training examples. There you can use any number of training examples. Just we stopped at 500. You can use any number of training examples, and you can do any function learning on this, right? The goal of this step 2 is basically we are trying to learn a function over these values, right? Now, this is a very simple thing to say. Okay, इसमें से minimum ले लो या इसमें से maximum ले लो. That's a very simple thing to do. But there may be a very complex kind of relation that exists between these values. We are not sure of that. So you can do any sort of function learning that. So these kind of classifiers allow you to do that kind of function learning. So we stuck to that. But you can do any kind of window based approach, or whatever works basically. So this was what is. So step 2 is basically once you have the feature values, you learn a function learning or classifier.
So can we say that in step 2 we are freeing ourselves from the choice of words, like words related to class?
You did horizontal scaling. You did that actually, right? But they obviously those feature values are coming from the words, right? So you are not really freeing yourself, but yeah, you are abstracting out basically, and you're also not going back to the LM. Okay, to fine tune it or change it or hit its pre-training. You're not doing anything on that. Whatever the thing said, you're learning something on top of that. That is the notion. So not exactly freeing yourself from the words, because the feature values are motivated from the key phrases, right?
So once we learn this classifier, would we still need the words?
For a test instance, right? If you do inference, you need to compute these feature values, right? So how will you do that, right? You have to have the key phrases. You have to go back to the LM to elicit those features, right? So you need them.
So the input to step 2 is going to be that only, right? The scaled features.
Right. So see, you can so you can see this. There is a training data set, on which you use the key phrases plus the LM to obtain the feature values, these perplexity and log likelihood values. So for the training data set, you converted that into a set of feature vectors. Simple. Now you learned the classifier. Okay. So now that ends the training part of the step 2. Now if you want to perform inference or do some kind of find for any test data, you want to apply that classifier, right? How do you convert the test data, the text in the test data, to the same form, right? Because your classifier will require those feature values, right? So you
Right.
have to have the key phrases and the LM ready. You pass the test data to that, you throw the test data to that, get those feature vectors for the test data, bring it to this classifier that you learned as part of the training, this thing, and then do the inference, do the testing, right?
Clear.
So you need,
Yes.
yeah. So step 2, I mean, the key phrases and the LM are not, I mean, you can't do away with that.
Right.
If you're thinking to do it, yeah, that is there, always there, right? Okay, so
Yeah.
yeah, so I hope that the thing is clear. Maybe I'll take the questions at the end because maybe we are short of time. I'll try to wrap it up quickly. Yeah, so we considered these 5 data sets. Okay, so this SST2 is a this yeah movie review kind of a data set where, and 2 means only positive or negative labels are there. There is SST5 also, which has more fine grained labels. There is Trek, which has different this thing. I mean, Trek has a very different kind of a thing. It is a classification of answer type. So basically, the instances are questions, and the label is what will be the answer like of this kind of a question, whether it will be a means of whether it will be a person, whether it will be a organization, something like that. In case of AG News, there are 4 classes: world, business, sports, and politics. In DBpedia, there are 14 classes. Again, they are means of transport, village, a place, location, something like that. Okay. And ethos is a very strange data set. It's on if you are interested to know, na, you can go and check what is the ethos data set. It's basically filled with racist comments, and different kinds of classification of these kind of comments, which are racist, sexist, whatever. And then it's a multi-label kind of classification. And these 8 labels, there's a star here. It's a real multi-label classifier. These are all single label tasks, but this is a multi-label. And the dagger here shows that we have chosen a subset of from the original trained data set, right? And this is also chosen from the subset. Right now, here there were only 433 instances in ethos at all. So we just divided them that. And there was a host of baselines that we considered, right? Zero shot with chain of thought, in context learning, classification, head tuning. So you keep the LM, you have a head on top of that, you tune it. Okay, tune the head, just the head, not the LM, right? The LM is frozen basically. Then you take an encoder like BERT and you train a classification head on the top of that, right? And there are 2 other things like this particular case of Min et al, which does this kind of noisy channel language model prompting, which was slightly similar to our approach. And there is this STNE paper, which does some form of unsupervised calibration or prior adaptation, right? So maybe you can read these papers. They are there in the presentation. I'll be sharing the presentation also, and you can have a look at these papers. And yeah, these were so now coming to that question with which Parth was asking, right? That what kind of, is there a limit on the key phrases or what, right? So now if you see Trek here, you see there is this abbreviation kind of a class. अब abbreviation को कितने की phrase डालेंगे हैं, तो we'll say an abbreviation, an expression which is abbreviated. So we did not think more out of that, right? So we just use these 2 key phrases. Okay, but say for world, which is a very generic class in AG News, you have to put in lots of key phrases: politics, terrorism, president, military related event, minister, elections, natural disaster, war or armed conflict, protests, religious event. You can put K things in that. There is no limit. But we just, in our thing, we limited it to 10 key phrases, but you can use any as such. You can see, right? Because now the approach is clear to you all. There is no limit on the key phrases. उतने ज़्यादा features बनेंगे, उतने ज़्यादा vector बड़ा हो. So there is no harm on that. I mean, there is no harm, in stopping the number of key phrases. हाँ, so now सबका interesting कि ये results कहाँ हैं? तो results यही है कि, I mean, obviously our techniques do perform better than lots of these baselines, and it even beats these kind of classification head tuning. This is proper training of a classification head, a neural training that I was just talking about. So even those are, ours is better that way. So this is like with all features and horizontal scaling. Even the zero shot baselines that we saw, right, without the step 2. Okay, these two are without the step 2. This is with step 2. So now without the step 2 also they are quite good. Okay, in case of SST2 we are reaching like absolute values are pretty good. Right? Or in case of ethos they are also pretty good, right? If you see here, and these people don't report the results on ethos, but from our baselines they are much better. And this is a multi-label classification into 8 classes, and for that if you get 4750 it's considered quite good. Okay, and with the SVM and the LR it reaches like about 70, like deployable performance. And yeah, and these guys didn't do the experiments on so these guys did the experiments on GPT-2 XN, which is like 1.5 billion parameters. Okay, but they didn't do it on GPT-2 Neo. I mean GPT Neo 2.7 billion, but we did that, so we are also able to compare on these lines, and we found that yeah, this seems to be better. Okay, again. So now this part is like when we vary the number of key phrases, okay, whether how good or bad it is. So if you see, if you use only one key phrase, the first key phrase in the table that I just showed, it does okay. But then after 3, 4, it starts plateauing. Okay, I have not shown the rest of the graph, but yeah, I mean, basically it starts plateauing. Similar is the case with training instances, right? We tried till 500, but when we started plotting it, okay, we after say 100, 150, 200 instances it started plateauing. So basically the training instances also stopped mattering. Okay, so just from the perplexity values, or it's trying to do fulfill that or learn the semantics of the class. And this is also some bit of ablation that we did if we remove the horizontal scaling, if you don't do the horizontal scaling, if you only use LL features, log likelihood, if we only use PPL features, if we remove the class level features, if we remove the key phrase level features, okay, or if you use only one key phrase per class, right? So still with all features and horizontal scaling it's better. But what we found was that sometimes without the PPL features, without the perplexity features, it does better. But this thing is not very good. I mean, this is similar and this is slightly better. So we can't say in very much certainty that yeah, removing the PPL features is a good idea. We don't know, right? And now one question would be कि ये connector sentence क्यों use किया ऐसा? So then we tried with different connector sentences also, right? The answer will be about, the answer is, the answer must be, the answer is about. So this is the track data set that I was talking about, right? So the text to be classified is a question, and the answer or the label is what is the answer type. Okay, so whether it's a human or whether it's a description of something, whether it's an entity, whether it's an abbreviation, whatever you say. Okay, so here we tried with all sorts of connector sentences, but I mean, we don't see any major difference, any major difference if we change the connector sentence. So the connector sentence is, and also if you see now exactly in this formula, right, the connector sentence is always in conditioning part. It is never playing a role in to determine the perplexity, right? So hence this is like also I should say sound that way. Okay, they are not involving the connector. This connector sentence is basically allowing us to make it a more readable kind of a thing, so that the LLM can produce the values properly, right? I mean, there is no. I could have just done Indian stock market gain on the third consecutive day dot economy, but that is not good, right? I mean, that is. I mean, it's weird to just link a word or just put a word without any connection to this. That's why we wanted the connector sentence, and it's obviously in the conditioning part, so it's all right. That is, we believe it's quite sound, right? And yeah, there is one more interesting of it, right? You can actually extend your classification decision using the key phrase, right? So if I say that this was classified as word, why was it classified as word? So you can say, okay, I take my PPL features, I just order them, and I say, okay, which key phrase was responsible? So terrorism आया. So it's really on terrorism, right? There was a fighting between the warlords in Afghanistan, and NATO airplanes had to retake the airbase. This is about terrorism. And then all this rally on the Wall Street, it's because of stock market. or top track athletes were they were named male and female athletes of the year. So it's 14 awards, right? Or trip to Mars, so space exploration. So if you see it, the right kind of phrases are coming as answers. So this is really explainable. Okay. And this was the main motivation. Okay, so now we had an case at our with one of the customers that we are trying to deploy something, and they wanted to do this kind of audit report classification. Okay, so where you have audit report and you want to classify each sentence, whether it talks about payables, receivables, inventory, fixed assets, human resources, whatnot. Okay, so there are I think 14 classes or something which we have to classify, and it's a multi-level kind of a classification. Okay, so where we did not have any data. So we, for the evaluation purpose, we created manually annotated these 10 audit reports to create this and then check. Okay, but for training data, we just use some sort of regular expressions to build training data, and then we applied our approach, right? So we saw that yeah, both this SVM and LR are doing quite well, even better than ChatGPT in a zero shot manner. Okay, ChatGPT zero shot. Okay, there is no I mean few shot also here, but it's doing better than this. Okay, though the mission is not to use ChatGPT, because this is all what should I say? This is all confidential data which should not go to ChatGPT or open APIs. But yeah, these were some open set of audit reports that we used, which is already available. There is a paper in 2014 which brings out this data set. So this analysis we exactly carried out on an open data set, but we are deploying this separately for something else where we are doing this. And there we are seeing that yeah, this kind of two-step approach that we are trying on a client in-house deployable model. We are using GPT Neo 2.7 billion that I was saying, and it's doing fairly well, right? It's helping, because what the real problem that they are having is that they have to sit with these audit reports and check कि अच्छा payables के बारे में कितना बात हुआ, receivables के बारे में कितना बात हुआ, right? Or what a particular company is lacking on. So its inventory handling is poor. So they have to sit and mark, okay, where we are helping, and we are already telling them that okay, just look at these sentences, these are so check between. So this is a real life application that. So I'll just end here. So of course you were all along, so you found this two-step approach for text classification, where you elicit perplexity or log likelihood based features and then learn a lightweight classifier on top of that. And if you could see, right, there was no limit on training examples, no need of parameter updates in the LM, no fine tuning was done, and explainability is there, and it's applicable in resource poor environments. I mean, for this particular task, we were able to, obviously this manual annotation took time, but we were quickly able to come with a classification model, because for each of these, we were able to create the key phrases with the person, the domain expert. And once we had the key phrases, we were there, right? We had the LM, we had the key phrases. Okay, text leke aao, do it using zero shot perplexity, right? So we were like quickly on with a classification model. And yeah, in future, and welcome to all. If you want to collaborate, you can come and then we can discover these optimal key phrases and connector sentences in an automatic manner. Okay, the topic modeling idea that I just said, and the kind of setting that we are in, right? The feature values that are there. You can use multiple small LMs to create that feature vector. Why stop at GPT Neo? Why stop at GPT XL? Right? You can use Falcon 7B. You can use a larger model to try. So all those are things that we are trying to do. And let's see if time permits, or if you guys are interested, then we can collaborate.